Let me start by thanking the organizers for inviting me to give a talk. It's the Hausdorff Institute for Mathematics. It's a great pleasure for me to here. And also thanks the organizers for organizing this workshop, which is part of the second NCG meeting, and may there be many more. So thanks to Kaad and Joachim and Francesca and Sven. All right, so I'm going to talk about compact quantimetric spaces, which is a line of research initiated by Eiffel back in the 90s. But I think it is very fair to say that an important part of Eiffels' inspiration and motivation came from the observation due to Kaad that if you have a compact spin manifold, then you can recover the metric from the Dirac operator. More precisely, all the relevant information about the metric is contained in the interaction between the algebra of smooth functions and the Dirac operator. Now, more generally, we can look at unital spectral triples, which we have learned over the past 30 years to think of as non-commutative geometric spaces. And in this setting, so once you have a unital spectral triple, then you have a canonical semi-norm on the core of the algebra, which measures the size of first-order derivatives with respect to the abstract Dirac operator. Now, this semi-norm, as we have seen yesterday too in Walter's talk, this semi-norm gives rise to a metric on the state space of the coordinate algebra, and it's an important question now whether this metric metrises the weak star topology. And in this case, we say that we have a spectral metric space. This terminology is due to Belisar and Marconi and Reihani. Okay, but if you say now you have two unital spectral triples, then there's a canonical tensor product construction available, which is called the Baj-Julg external product. And this external product is compatible with the external product in analytic homology. And moreover, if you start out with two compact spin manifolds, and you look at the corresponding unital spectral triples, you carry out this external product construction, then you recover the Dirac operator on the Cartesian product of these two compact spin manifolds. In particular, you can recover the correct metric on the Cartesian product via this external product construction in the case of compact spin manifolds. So therefore, it makes sense to ask the following question. Is it true that if I start out with two spectral metric spaces, is it then true that their external product is again a spectral metric space? So that's going to be the main research question for this talk. And before we can get that far, I'm going to present some background material and also show you a novel characterization of what it means to be a compact quantum metric space. This novel characterization proceeds via finite dimensional approximations. So here we go with the first slide. So I'm constantly talking about states on operator systems, even though Eiffels' original work was carried out in the context of order unit spaces. But here we work with operator systems. Okay, so what is an operator system? This is going to be a unital subspace of a unital C-star algebra, which is also star invariant. So whenever I have an element inside X, then the adjoint also belongs to X. Okay. Then I can say what it means to be positive inside X. This means that you are positive inside the surrounding unital C-star algebra. So what it means to be positive in X is controlled by the positive cone inside A. And then states. So states are linear functionals on X is also positive, and they map the unit to the unit. And I can talk about the state space. It becomes a compact Hausdorff space when equipped with the weak star topology. So notice here that my operator systems, they are not complete. But if I take the closure of X in C star norm, then I get a complete operator system, and the state space of this operator system is the same as the state space of X. Yeah.
Does the unit depend on X? Where do you?
Yeah, it's just it is the unit inside A. It just sits inside X. Yeah.
Yeah. So one A, not.
Yeah. That's okay. Yeah, but the inclusion of X into A is unital. Yes. And okay, so I'm interested in metrics on state spaces for operator systems, and in particular on those metrics which rise the weak star topology on the state space. And now it's a key observation within the theory of compact quantometric spaces that you can construct metrics on the state space from semi-norms on the operator system. And I'm in this talk mainly interested in so-called Lipschitz semi-norms. And here comes the definition. So this is going to be a semi-norm on an operator system, and it has to be star invariant, so it doesn't see the difference between X and its adjoint. And then it has to vanish on the unit. It's the same thing as the unit in A. Now, it's perhaps more common to say that a Lipschitz semi-norm satisfies that the kernel of L agrees with the scalars. But here, for the purposes of this talk, it's more convenient with this more flexible definition where the kernel of L just contains the scalars. We shall see many examples in this talk where the kernel of Lipschitz semi-norm is much bigger than the scalars. Okay. And now we're ready for the definition of a compact quantometric space. You've seen it earlier in this workshop and last week too, but here it comes again. And it proceeds via the so-called Mons-Kantorowicz metric. Defined as follows. So I have a Lipschitz semi-norm on an operator system, and then I can write down a metric on the state space of this operator system. But okay, so notice here that it's really an extended metric. So it can take the value infinity, but otherwise it satisfies all the usual properties of a metric, but it can happen that the distance between two states is equal to infinity. And here's the definition. So if I plug in two states, mu and nu, then the distance is defined as a supremum. I look at the distance between all possible values of the two states under the condition that the semi-norm of the input is dominated by 1. Okay, and then we say that the pair here, consisting of the operator system and this Lipschitz semi-norm, this is a compact quantometric space. It means that this Mons-Kantorowicz metric, it metrises the weak star topology on the state space. Okay.
The definition for metrises this.
When you have a metric, then you get a topology. This topology has to agree with the weak star topology. Yeah. So weak star topology is pointwise convergence of states. Okay, so suppose now that you give me an operator system and a Lipschitz semi-norm. How on earth do I check whether this is a compact quantometric space or not? This could be potentially a difficult question to settle because the state space could be complicated, and if I look at two states, it could be next to impossible to compute the distance between these two states. But luckily there's a characterization due to Mark Riefel which allows me, so characterization of what it means to be a compact quantum metric space, which allows me to disregard the state space altogether and work directly with the operator system and the seminorm. And it comes here. Okay, it appears that this characterization was also found by Branka Pavlovich at around the same time, but I think that she got the problem from Riefel. Okay, so to be on the safe side, I also put her name on this theory. I don't know the exact story. Here it is. So saying that this operator system and the Lipschitz semi-norm is a compact quantum metric space is equivalent to the following statement. So one has to check that a certain subset is totally bounded. And this subset, it lives inside the quotient space where I mod out the scalars from X. And this quotient space is equipped with quotient norm coming from the C star on X. So with respect to this norm, it has to be totally bounded, this subset, and the subset is given by the image under the quotient map of the semi-norm unit ball. So that's the subset I have to look at. This has to be totally bounded. That's equivalent to having a compact quantum metric space. It's also positive to characterize what it means to have, for the state space, just to have finite diameter. And this is equivalent to saying that my subset up here is bounded. Then I get finite diameter.
Totally bounded mean?
Totally bounded means that whenever I'm given an epsilon, then I can cover this set with finitely many balls of radius epsilon. That's totally bounded. It's not complete open. But if it were complete, then yeah, it's the same. I prefer totally bounded. Yeah, so having finite diameter means that this subset here is just bounded. Now I'm going to phrase this in a slightly different way because of a point I want to make later on. So the state space for X equipped with this Morse-Kontorowicz metric has finite diameter. It's equivalent to saying that I can find a constant such that there's an estimate which is valid for all elements inside my operating system. And on the left-hand side, I just have the quotient norm of the corresponding equivalence class. On the right-hand side, I have my constant C times the Lipschitz semi-norm applied to X. That's equivalent to having finite diameter. And I think that David will tell you tomorrow that having finite diameter actually happens if and only if the distance between two states is never equal to infinity. And that turns out to be equivalent. But that's just a little bit, that's a little teaser for David's talk. Yeah. Now, I told you that I was going to give you a novel characterization of what it means to be a compact quantum metric space. And it turns out that this theory of compact quantum metric spaces is very deeply related to finite dimensional approximation problems. And to explain the statement, I'm now going to introduce a particular kind of finite dimensional approximation where the precision of the approximation is controlled by one of these Lipschitz semi-norms. It comes here. Yeah. Okay, so I start out with a positive number epsilon, and then I will say that my pair consisting of the operator system and this Lipschitz semi-norm admits an epsilon approximation. What does this mean? It means that I can find two unital linear maps, J and phi, with values in an oscillatory operator system set. And they have to satisfy three conditions. So the first one is that iota is isometric, and phi, which is going to be the approximation, is positive. Okay. Yeah, and they're still unital. This is very important. The second one says that the image of the approximation phi has to be finite dimensional. So phi is finite dimensional image inside set. And the last one is about the precision of the approximation. It says that that's an estimate on the error term here. Says that whenever I have an element inside my operator system, then the C star norm of iota of x minus phi of x is dominated by epsilon times the semi-norm applied to x. And I want to show you a little example of such an epsilon approximation just in the case of a compact metric space. So you can see what it looks like. That comes here. Okay, so let's just look at a compact metric space. So M and the metric is called rho. And I'm going to fix epsilon. So I'm going to construct an epsilon approximation of my data. So I have an operator system. It consists of all the Lipschitz functions sitting inside the unital C star of continuous functions. And I also have a Lipschitz semi-norm on this operator system. When I plug in a Lipschitz function, it spits out the Lipschitz constant. So that's my Lipschitz semi-norm. I'm going to look at the pair consisting of Lipschitz functions, an operator system, equipped with this Lipschitz semi-norm, which computes Lipschitz constants. Now I want to construct an epsilon approximation of this pair. What do? I choose an open cover of M. I open balls of radius epsilon. I can do that because it's compact. And then I choose a partition of unity, which is subordinate to this cover. So the support of function psi j is contained inside the ball of radius epsilon in center pj. Okay. And now I'm going to define my approximation. So first, the map iota, the isometry, is going to be the inclusion of the Lipschitz functions into continuous functions. And my approximation phi does the following. So when I evaluate it on a Lipschitz function, let's get the sum over here where I have evaluated f, the centers of my open balls, and I multiply with the corresponding positive function from my partition of unity. And this pair consisting of iota and phi is going to be an epsilon approximation of the Lipschitz functions with this semi-norm, computes Lipschitz constants. So I can see here that this pair down here is an epsilon approximation for every positive epsilon. That is no coincidence because of the first main result of this talk. It is a characterization of compact quantum metric spaces in terms of finite dimensional approximations. So there are having a compact quantum metric space x, L is equivalent to the following condition. Namely that my pair has finite diameter and I can find an epsilon approximation for every positive epsilon. So that's the same as having a compact quantum metric space. So in this talk, the main focus actually lies on compact quantum metric spaces of a non-commutative geometric origin. It means that the semi-norm in question comes from a unital spectral tuple. What does this mean? I'll start with a unital spectral tuple. Then I can always define a derivation d on the coordinate algebra the derivative of an element A is just the closure of the commutator between the abstract Dirac operator and this element A. And this gives rise to a semi-norm. On the coordinate algebra, the semi-norm just computes the operator norm of the derivative of A. And it can be verified that this is one of these Lipschitz semi-norms. I'll then say that a unital spectral triple is a spectral metric space. This means that this pair consisting of the coordinate algebra and the semi-norm up here, Lipschitz semi-norm up here, that this is a compact quantum metric space. So here I'm actually forgetting the algebra structure on A. I'm just thinking of A as an operator system sitting inside the bounded operators label space. Yeah. I'm then particularly interested in tensor products of compact quantum metric spaces. And this becomes very interesting in the context of spectral metric spaces, because if you have two unital spectral triples, then there's a canonical tensor product construction available, which is called the external product. And I'm just focusing here on the even case, but there are similar constructions available for other combinations of cases. Let's see what it looks like. If we have two unital spectral triples, AHD and BDE, they are both even, then I can construct a new unital spectral triple, which is also even. So I have a new coordinate algebra, it's a tensor product of A and B. It acts on Hilbert space, which is a Hilbert space, tensor product of H and G. But notice here that this is Z mod 2Z graded. The grading operator comes from the tensor product of grading operator by H with the grading operator for G. I'm in the even case here. And then I have this unbounded product operator, the last ingredient, which is an odd self-adjoint unbounded operator in this Hilbert space. It's defined as the closure of a symmetric unbounded operator, which is sometimes it's also called the tensor sum. So that's given by the following explicit operation here. I take d tensor 1 plus gamma tensor E, where gamma is a grading operator on H. And the domain here is the algebraic tensor product of the two domains. Take the closure of this one, and I get this unbounded product operator d times E. And then it's a theorem due to Marsh and Schulk that this external product is again an even unital spectral triple. And moreover, they have clarified that this construction is compatible with the external product in analytic cohomology via the so-called Marsh-Schulk bounded transform. Okay. And now we're ready for the main question. As I mentioned also in the beginning of this talk. Yeah, so suppose you have two spectral metric spaces. Is it then true that their external product is again a spectral metric space? So I should tell you here immediately there are many examples of unital spectral triples which are not spectral metric spaces. They are not hard to construct, and I think also tomorrow you will see an interesting example of such a unital spectral triple which is not a spectral metric space. It's a valid question. That's what I'm trying to say. And I spent quite some time thinking of it until I realized that I didn't even understand what happens to a spectral metric space when you stabilize it with scalar matrices. And that was a depressing moment for me. So I started doubting my skills as a mathematician until I realized that perhaps I should try to incorporate this operation of tensorizing with scalar matrices into the theory of compact quantum metric spaces. And people in the audience who who know about operator spaces will certainly recognize Rand's fundamental idea of an abstract operator space in my next definition of a Lipschitz operator seminorm. It comes here. Okay, so again we have just an operator system. So X is a star invariant unital subspace of a unital C star. And now I want to, what is an operator seminorm on an operator system? Well, that's a whole sequence of seminorms, one in each degree. And the seminorm in degree n, it lives on matrices of size n, with entries in this operator system. And then there are two compatibility relations which have to hold. The first compatibility relation is about matrix products. So here I have V and W are scalar matrices, and X is a matrix with entries in the operator system X. And I can look at the matrix product of V times X times W. It's again a matrix with entries in X. And I can apply the seminorm degree n to this matrix. And this has to be dominated by the C seminorm of V times the seminorm applied to X times the C seminorm of W. That's the first condition. The second one is about direct sums. So if I have two matrices X and Y with entries in X, say they are of size n and k, then I can form that block diagonal direct sum and apply the seminorm in degree n plus k to this block diagonal direct sum. And this has to agree with the max of the two seminorms applied to the two factors. In this case, I say I have an operator seminorm. And I'll then say that I have a Lipschitz operator seminorm. It means that all the seminorms in my sequence are Lipschitz seminorms. So all the seminorms in the sequence are star invariant and vanish on the unit. Okay, notice here that once I have a Lipschitz operator seminorm, in the kernel of the seminorm in degree n automatically contains all scalar matrices, not just scalars. So the Lipschitz seminorm in degree n has a larger kernel than just the scalars. It automatically contains all scalar matrices. And a key observation is now that if I start out with a unital spectral triple, then I automatically have one of these Lipschitz operator seminorms and not just the Lipschitz seminorm. How does that go? Because if I started with a unital spectral triple, I can always stabilize it by scalar matrices. And I get a new unital spectral triple. The new coordinate algebra is given by matrices of size n with entries in A, and it acts on the n-fold direct sum of H with itself, and the new Dirac operator is given by the n-fold direct sum of D with itself. So we saw earlier that whenever I have a unital spectral triple, I have a Lipschitz seminorm. So I have a Lipschitz seminorm in each degree automatically. How is it defined? Well, I apply the derivation little d entry by entry, then I compute the C star norm of the corresponding matrix of operators. That's what this seminorm does. Does that make sense? Little d comes from the spectral symbol I start out with. That's derivation associated to d. When I apply that derivation entry by entry, get a matrix of operators, I can compute the C star norm. That's the same as the seminorm coming from this stabilized unital spectral triple. And then it can be proved that it's really very easy to do that this is an example of a Lipschitz operator seminorm. So whenever I have a unital spectral triple, I have a canonical Lipschitz operator seminorm, not just a Lipschitz seminorm. Okay. Now, the key property of these Lipschitz operator seminorms, which is not available when I just look at Lipschitz seminorms, is that Lipschitz operator seminorms are compatible with minimal tensor products. And that comes here. Okay, there's a little bit of extra terminology first. So now I have two operator systems, X and Y. I consider their algebraic tensor product as an operator system again. How so? Well, it sits inside the minimal tensor product of the two unital C-star algebras A and B. So what it means to be positive inside this algebraic tensor product is determined by the positive cone inside this minimal tensor product of A and B. This is a minimal tensor product of operator systems I'm looking at. And I'm going to use some slice maps. This is an awful lot of information, but I'll go through it slowly. So say I started with a UCP map, a unital completely positive map on the second factor y. And it takes values inside scalar matrices, say of size k. Then I have a slice map, which is called 1 tensor phi, defined on this tensor product and with values inside matrices of size k over x. How is it defined? Well, on a simple tensor, 1 tensor phi maps it to this k-fold direct sum of x with itself, multiplied with phi of y. I just multiply all entries in phi of y with x. And this slice map can then be extended to matrices with entries in this minimal tensor product. In degree n, how is it defined? Well, I just apply 1 tensor phi entry by entry, and I get a matrix of size n with entries with some matrix of size k over x. And I can just forget the subdivisions. I get a matrix of size n times k over x. So that's the extended slice map, and it's going to play a key role for defining Lipschitz operator seminorms on minimal tensor products. So let's see. Now I have two Lipschitz operator seminorms, L and K, one on x and one on y. Okay. Then I'm going to define a Lipschitz operator seminorm called L tensor 1. It's going to live on the minimal tensor product of x and y. And I have a similar construction which gives me 1 tensor k, but I'll just focus on L tensor 1 here. How's that defined? Okay, so L tensor 1 is going to be one of these Lipschitz operator seminorms, so I have to tell you what it does in each degree. In degree n, this seminorm here lives on matrices of size n with entries in the minimal tensor product. Okay. So if I have such a matrix, what does this seminorm do? It has to spit out a number. Okay, so if I now have a UCP map phi on the second factor, with values in scalar matrices, size k, say, then I can apply this extended slice map to Z, and I get a matrix of size n times k with entries in x. So I can apply the seminorm in degree n times k to this matrix, I get a number. And seminorm in degree n for L tensor 1 is just the supremum of all these numbers. And that's going to be a finite quantity. And it can be proved that this sequence of seminorms is in one of these Lipschitz operator seminorms. And there's a similar construction available for 1 tensor k. Yeah. If I have a Lipschitz operator seminorm, then I can extend it to minimal tensor products.
Yeah. I mean, some of the obvious idea would be, okay, let's take a tensor and decompose it to, I mean, like a projective tensor product. Yeah, you use some more minimum over all elements.
It's not a projective tensor product.
Yeah, but I mean, this wouldn't work.
This one, I'm using this one because something which I'll not show you, but I can tell you that this is really the construction which is well behaved when you look at spectral triples. So if I start out with a spectral triple where the coordinate algebra is A, okay, and I have another algebra B, some operator system B, sitting inside bounded operators on another Hilbert space, then I can look at the abstract Dirac operator D tensor 1 acting on Hilbert space tensor product. And I can use that to construct the Lipschitz operator seminorm. And that construction will give me the same output as this one, but here without talking about spectral triples. That's why I'm doing it in this way. That's a very good reason for it.
Just a small question. The soup here is okay and 5.
Yeah.
Yeah.
Yeah. Yeah. So now I'm going to tell you about a matrix version of my finite dimensional approximations. These are called matricial epsilon approximations. And the idea is here that the error term, so the definition is very similar to what you saw earlier, the definition of an epsilon approximation. But now there's an important difference, namely that the error term is controlled by a Lipschitz operator seminorm in a way which is independent of matrix size, which we didn't have before. So I start out here with, again, a constant epsilon, and then I say that my operator system equipped with a Lipschitz operator seminorm admits a matricial epsilon approximation. What does this mean? So it's almost the same definition. I have two unilinear maps, iota and phi, with values in an auxiliary operator system set. And then I now say that iota is completely isometric and phi is completely positive. Before they were just isometric and positive. Now I put in an extra word. Second one is the same as before. The image of the approximation is finite dimensional. And the last condition is about the estimate on the error term. So this estimate has to be independent of matrix size. So it has to be valid for all natural numbers and all matrices of size n with entries in the operator system. So here's the C star norm of iota of x minus phi of x. Here I'm just applying iota and phi entry by entry. So I end up with a matrix of size n over Z. And the C star norm is to be dominated by epsilon times the seminorm in degree n applied to x. So once I have such iota and phi, I say that my pair admits a matricial epsilon approximation. And I can now also say what it means to have uniformly finite diameter. That's my second definition. Walter, yeah.
So if you would kind of forget about the ambient C-star algebra, would you still make sense of this definition?
Yeah,
I mean, so do you need some kind of matrix norm, or can you?
Yeah. So it will also make sense for abstract operating systems. Yeah.
And then you take a matrix
But
norm.
I need to know about the norm on matrices over Z.
Which you may get from the operator system, right?
Yes.
Unital anyway. So.
I could have formulated all this abstractly too. There's no also abstract minimal tensor products. It's just to make it slightly more complete.
No, but of course you are in a dense subspace, so one has to kind of maybe. So this minimal tensor product would be the completed version. But anyway,
not necessarily. Yeah. Okay. Okay, so I can also make sense of having uniformly finite diameter. That's my next slide. and then you'll see theorems afterwards and examples. So this pair, X is an operator system and L is a Lipschitz operator semi-norm, has uniformly finite diameter. This means that I have an estimate of all the various quotient norms in terms of the Lipschitz operator semi-norm, and this estimate is independent of the matrix size. Okay, so what does it say? It means that I can find a constant C. So I said there's an inequality which is valid for all natural numbers n and for all matrices of size n over X. And on the left-hand side, I have the quotient norm of the corresponding equivalence class. And on the right-hand side, I have my constant C times the Lipschitz semi-norm at degree n applied to X. And here, notice that I'm not just modding out by scalars. I'm modding out by scalar matrices for this quotient norm here. And that is because the kernel of this Lipschitz semi-norm automatically contains all the scalar matrices. So in order for this estimate to make sense at all, I have to mod out by scalar matrices. That's uniformly finite diameter, and combining the property of having uniformly finite diameter with the existence of arbitrarily precise matricial approximations, get the notion of a matrix compact quantum matrix space. So I say that my pair X, L is a matrix compact quantum matrix space. This means that it has uniformly finite diameter, which you just saw, and this pair admits a matricial epsilon approximation for every positive epsilon. So I have a matrix compact quantum matrix space, and this definition also makes sense in a non-commutative geometric setting, because if I start out with a unital spectral triple, I have a canonical Lipschitz operator semi-norm on the coordinate algebra. So I can talk about matrix spectral metric spaces. They are unital spectral triples, such that the coordinate algebra equivalent is Lipschitz operator semi-norm is a matrix compact quantum matrix space. Yes, and the key selling point is now that matrix compact quantum matrix spaces are compatible with minimal tensor products. And that's the main theorem of this talk. So suppose that I have two matrix compact quantum matrix spaces, X, L and Y, K. Then I can look at their minimal tensor product and equip it with a Lipschitz operator semi-norm, which is a max of L tensor 1 and 1 tensor K. And this pair here is in a matrix compact quantum matrix space again. The minimal tensor product of two matrix compact quantum matrix spaces is again a matrix compact quantum matrix space in this precise way. And this theorem can be translated into the world of unital spectral triples. In that context, it says that if I have two matrix spectral metric spaces, then the external product is again a matrix spectral metric space. So if AHD and BGE are matrix spectral metric spaces, then the same is true for the external product automatically. And finally, to convince you that I'm not talking about nothing, it could be that I had no examples of matrix compact quantum matrix spaces. I have collected a little list of examples of matrix compact quantum matrix spaces. You can see there are various people attached to these examples. These are the people who showed that they are examples of compact quantum matrix spaces. I have then done a little bit of extra work, and I've been able to show that they are actually examples of matrix compact quantum matrix spaces. And this reference here is slightly wrong. It's more correct to mention Erik Christensen and Christina Ivan for the example of AF algebras. Yes, and it's also another way this list is incomplete is that I didn't put the Lipschitz operator semi-norms in my list because it became too messy. But if you're interested, then you can just contact me, and then I can tell you more about these examples. I also think there are many more examples of matrix, compact quantum matrix spaces around, but these are the ones I'm aware of until now. So that was everything I wanted to say. So short talk. Thanks for listening.
Questions? So do we have questions or comments? Yes, please.
Example of the compact thing which is not matrix compact?
Actually, I don't know one yet. No. So, but I mean, you need to come up with a Lipschitz operator seminorm instead of a Lipschitz seminorm. But I currently I don't have examples, and I think it's not that easy to find.
Yeah, so given that external products in the world of spectral triples are rather simple, it's a bit surprising that it's so difficult. It seems to be so difficult in spectral metric spaces. This is maybe due to the fact that if you have the state space of a tensor product of algebras is not necessarily a product form.
Exactly.
Kind of
Yeah, the state space of a tensor product
yeah.
can be complicated.
Yeah.
But, I mean, yeah.
I mean, you would say this is the underlying reason why things get more complicated. Or is there a different?
Yeah, I mean, you have this theorem still, but you seem to need this little bit of extra information regarding matrices with entries in the coordinate algebra, not just knowledge about the coordinate algebra itself. Okay. Time will tell whether all spectral metric spaces are actually matrix spectral metric spaces, and then it's great, of course.
There are these results about completely symmetric embeddings of operator spaces or operator systems. I suppose you probably can apply this in your case. And is your minimal tensor product then just the obvious, so this L tensor 1, is it just the usual tensor product on the Hilbert space level? That sounds plausible to me that it should come out like this, but is this how you got at it, or?
I'm not so, that could very well be the case, but it's only, I mean, the first factor is just a seminorm.
Well, I mean, you can just take a quotient. I mean, there are these people have written books about these operator spaces or written like quotients and duals and whatever. And I suppose you have just the quotient with an induced norm. And then, well, if you oppose enough axioms, this embeds completely symmetrically. I've forgotten what the axioms are, but you might want to check. You can tensor them spatially in a concrete way. And I would guess people have studied whether this is well-defined, independent of realizations.
I think you are.
Also, that you get something like what you have done there. You might get what you have done there in a kind of more natural or appealing way.
I agree that one can perhaps describe this Lipschitz operator seminorm L tensor 1 using known tensor product constructions. That is very likely to be true. I haven't investigated it in details.
So, have you looked at what do you get, for example, if you apply your tensor product result to, let's say, those AF algebras, what do you get? No spectral difference.
Well, I mean, you have this canonical tensor product construction for spectral triples, and that's, I mean, you get a result about the corresponding seminorms. It's, yeah, I don't know what you're looking for.
An example of the theorem, I mean, where you do get this tensor product that gives you something.
Yeah, I mean, you can take tensor products of any of those. Yeah, I don't know what they're looking for.
So, in what sense? Yeah. So, when
I think yes. Yeah, definitely. Yeah.
So are these operator Lipschitz seminorms in some way corresponding to metrizability of matrix states, or are they seemingly unrelated?
That's a very good question. I mean, I haven't been thinking about it. I mean, I can characterize in terms of matrix state spaces what it means to have uniformly finite diameter. But I don't know how to characterize a matrix compact non-matrix spaces. So the second part about matricial epsilon approximations, I haven't been able to settle because of this. I mean, because you need to know that this embedding here, it also has to be completely isometric. And that's tricky. Combined with also having 5-dimensional image. Yeah. So that's a very good question. I would love to know more about it.
Is it conceivable you could do a version of this for an internal type product, like the non-commutative torus, for example, is a circle bundle over a circle, like, you know, it's sort of nearly an external product in some sense, right? But is it that plausible with the technology that you built to?
Yeah, that's another very good question. I mean, the way I was thinking of this to begin with was that I would like to understand how does the unbounded Kaad product relate to compact quantum metric spaces. And then I thought, okay, I better understand the external product first, because this is something I can maybe do. But currently there's no bivariant theory of compact quantum metric spaces available. So yeah, that's something which needs to be investigated.
Again, back to this tensor product. I mean, if you just want to find tensor product of XA with Y, two such things, then I don't know what the L was for the K, Then I mean, in the case of a compact quantum metric space, we have finite dimensional approximations on Y, so it's fine. But somehow in general, if you don't have enough Y's, finite dimensional approximations, then I mean, what comes out? What is the universal property of this sort of tensor product? I mean, you don't generalize to compact quantum metric spaces.
I'm not sure I understand it.
I mean, you need a lot of phi's to have a good, probably you need a lot of finite dimensional, I mean, you need finite dimensional approximation for Y in order to.
Yeah.
So what happens if you don't have this?
I mean, we can discuss also, and that's maybe also related to Ralph's question. I mean, I could, maybe that was what you meant. I'm not sure, but I will try to answer what I think you meant. What if I use fewer of these maps?
No, I mean, if you don't have enough, I mean, somehow if the Y is bad, does not have finite dimensional.
But this is just state. I think you always have these maps.
These you always have, yeah. But that's so if you just so if you don't know anything about Y, if you look at X tensor Y, but you have information about X, what kind of object do you get from this L tensor 1? Is that what you mean? Yeah. That's a valid question. Yeah. So I mean, one could try to analyze X tensor Y just equipped with L tensor 1 as a kind of bivariant of a quantum metric space over Y. That's a sensible thing to do. Okay, maybe you can talk about it afterwards.
Mike first.
So if memory serves, Christensen and Ivan were after spectral triples on Sierpinski gaskets, and I wanted to take AF algebras of circle algebras. So I guess your result just completely generalizes this. Is that right?
So I think I can show that they have examples of matrix spaces. So you can do tensor products as you want.
And you just take the circle spectral triple and tensor it with the AF algebra.
Yeah. That's going to fall out immediately.
And probably you get other fractals this way too, I guess.
Ralph, I think also, yeah.
Since you come from this Dirac operator situation, I was so surprised to see your maximum of one tensor L, and so I would rather think to do something like a L2 sum of these two things instead of a max
It's just a choice I made. It doesn't really matter. But okay, I think it's okay. So if you think okay, so that's about this slide.
Since you work with complete isometries in your definition, somehow it should make a difference which of these equivalent norms you choose. It doesn't look like the correct spatial, or it doesn't seem to match your Dirac operator construction in the spectral triple world.
It's related to the question, if I have two compact metric spaces, what is the correct metric on the Cartesian product?
Of course, there's many choices.
You can do many things, and this is just one choice, but down here, this construction is canonical. And you prove this theorem via this one.
Yeah, but
So it's a kind of
continuing that question. I mean, the Lipschitz norms that you get for the tensor sum, how is it related to the max?
yeah. So it's not the same as the max at all.
How do you deal with that? I mean, then
You have an inequality.
yeah, okay. So that so this is
so.
Is there a formula that always works? I mean, in the manifold case, I know what I get, but if you don't have a manifold, is this still an L2-like thing, or can it be anything?
with the grading. I think you can write some formula.
Okay, so this is just one possible choice, but there are many others. And there's no, it seems like in this generality, there's no canonical choice. But down here, there is one. And,
Okay.
I have one more, I'm sorry. Have you thought about Kunis formulas for this at all?
I just finished this.
Yeah,
you could do plenty of things. It's,
One more question or something? Yeah, you had one. Yeah.
So I guess like the dual to Cartesian products of convex sets isn't the tensor product, right? It's this co-product. If you look,
the problem.
well, so there's a result, I guess due to Kerr and Lee and recently as well. Let's say if you take two matricial states and you take the Cartesian product, then the matricial affine functions on that is actually the co-product. It's not the tensor product. This is somehow it's the tensor is the wrong intuition here, I guess.
If I take continuous functions on compact metric spaces and I take tensor products and I get the continuous functions on the Cartesian product.
But this is a convex set now, so it's. We can sorry, talk about it.
I think for states it's different.
Yeah.
I mean, for the states you will get something, as you say. But if you think about A and B being commutative, then it's like a spatial construction. That's, I think, why when we take the minimal tensor product.
Other comments?